Hello again, and welcome back to IPC class. I hope you guys are all handling this online work well. I have enjoyed those of you who have dropped by either for tutoring or just to chat or a game of Mancala. I kind of enjoyed having you guys just come in and chat with me. So, the last section of this chapter is called Laws of Thermodynamics. Now, these are a little bit harder to grasp than other ideas in physics, but they're also some of the most important. They underlie a lot of things that happen in our society, from car engines to air conditioners and refrigerators. All of those are run by the laws of thermodynamics. So, the 0th law of thermodynamics. This one is not in your book. This is extra information. It's typically not introduced to high school, but you guys can handle it. It's called the 0th law, I think, because it was so basic, people didn't realize it needed to be stated until people weren't getting it. Okay. So, object A, B, and C. You've got three objects on the screen: a circle, a triangle, and a pentagon. So let the circle be A, the triangle be B, and the pentagon be C. What the 0th law of thermodynamics means is that if A is in equilibrium with B, when we say equilibrium in terms of thermodynamics, we're talking about at the same temperature. So if A and B are at the same temperature, and then if B is in equilibrium with object C, in other words, B and C are at the same temperature, then A and B, the circle and the pentagon, have to be at the same temperature. Now, I know that seems really basic, doesn't it? So let's think about that in the context of a real world thing. It's getting warm, summer's coming on. Me personally, when I'm here at home, I don't always sit in my office. I like to go outside and sit in my backyard when I'm working. So consider I have my little ice chest full of ice, and let's say my husband's sitting with me. So I put a Dr. Pepper in the ice for him. And as we talked about last time, the heat exits the Dr. Pepper into the ice until the Dr. Pepper and the ice are at the same temperature. Meanwhile, I like Pepsi. I know I'm a northerner, deal with it. So I put my Pepsi in the same thing of ice. And my Pepsi loses energy, loses heat, until it comes to the same temperature as the ice. So now you have the Dr. Pepper at the same temperature as the ice, at the same temperature as the Pepsi. That means that Dr. Pepper and Pepsi, they're at the same temperature too. That's all the 0th law is saying. Seems really simple, doesn't it? All right, then we get into the first law of thermodynamics. First law of thermodynamics says that the total energy used in any process is conserved in the form of work, of heat, or both. All right, first of all, let me make this really simple. Remember the law of conservation of energy that we learned last chapter? Remember the skateboard park? Back and forth on the skateboard, start at the top of the ramp, down turns into kinetic energy, up turns into potential energy. All the first law of thermodynamics does is expand on that idea of law of conservation of energy. Remember that work is just energy being used. So, heat energy can do work, and work can generate heat energy. It's a back and forth process. So, work can change the kinetic energy of an object. Really simple little deal here. Take your hands, put them together, rub them really hard. You are doing work rubbing your hands together, okay? Now, take your hands, feel your cheeks. Do you feel them getting warm? Well, what that is as you were rubbing your hands together, the cells, the atoms, the molecules, and the surface of your hand were increasing in their kinetic energy. All that carbon and phosphorus and whatever else, oxygen that makes up your hands, was starting to vibrate faster and faster. Well, work, rubbing, changed into kinetic energy. You sense that when you touch your cheeks as heat, as temperature. Here we are to do a little experiment to show heat and temperature in the first law of thermodynamics. Now, you can do this at home with your parents' approval because you are playing with fire. Okay. All you need is a small plate. This is a salad size plate, not your normal dinner plate, but not your saucer. Water, and all I did was put some red food coloring in this so that you can actually see what the water is doing. And then a small candle, and you can see I've already got it lit, and a glass. Now I found playing around with this that a tall skinny glass works best. I tried short fat glasses, but this one seems to be the one that works the best for this experiment. So it's a little windy out here. You want to get that candle burning pretty well. Keep in mind, if you remember back to last semester, this is a chemical reaction happening, combustion. So we're taking the chemical energy from the candle and turning it into heat and light energy. Now, what I'm going to do here in a minute is to put the cup over the top of the candle. As you can imagine, the candle will burn through the oxygen that's inside the cup, and it will start to go out pretty quickly. But what's important is what happens while that is burning inside the cup. So when we put the glass over the candle, let's try that again. When we put the glass over the top of the candle, think about what's happening inside as far as energy. That heat energy generated by the candle is being absorbed by the air inside the cup. So now the air inside the glass is heating up. Now watch what's happening right down here at the bottom. So the candle starts to go down, it's burning through its oxygen. Okay. The air up here inside the glass is heating up. The candle just went out and ooh, look at that. So that water got drawn up inside the cup. That is work being done by the heat of the air inside. So the air inside the cup got nice and warm. But heat energy doesn't stay where it's warm. It moves from hot to cold. Now that's the second law of thermodynamics. Back to the first law of thermodynamics, where did the kinetic energy in the atoms and molecules of the air go? Well, it got absorbed into the glass, got absorbed into the water. And if you remember our discussion yesterday, as fluids warm up, they expand, but as they cool down, they condense. And so as the air inside the cup cooled down, it condensed, and it took up less space. Well, there's an old saying that nature abhors a vacuum. That means that you can't just leave empty space. If the air condenses, something has to fill it up. And so that's what drew the water up inside the glass. As the air condensed, it created lower pressure, and that lower pressure allowed the higher air pressure outside to push the water down and up inside. So the air inside the glass, by giving up its energy, by transferring that energy, caused work to happen. So that's the first law of thermodynamics, that heat energy can be used to do work. Now in this case, the heat energy was being lost from the system. It can also be gained into the system. If you could imagine that somehow magically I refilled this thing with oxygen and relit the fire, it would then push that water back out. Now, I don't have the means to do that, but you could imagine that. So take a look at a car piston. Okay? Car piston makes basic use of this. There's 4 strokes in a basic car engine. Okay? Typically, your car is going to have at least 4 cylinders, so 4 things that look like this. Your really big, powerful Dodge, Hemis. The biggest trucks they can have up to 12. Don't ask me about semi-trucks. I don't know what they have. Okay, but 4-stroke piston is what this is called. The first stroke, number 1 right there, the fuel and the air come into the piston, and you notice that, come into the chamber, and you notice that in 1, the piston is going down. So there's room for your fuel and your oxygen to come in. And then that valve closes. So step 1 right there is the fuel and air coming in. Okay. Step 2 is the piston ramming back up. So as that comes up, right here, pushes, okay, that upstroke takes that fuel and air and compresses it. Well, when you compress fluids, they actually get hotter. So the work of that piston coming up becomes kinetic energy in that hot mess of fuel and air. Now, step three is a downstroke. On step three, this is where your spark plugs. You may have heard people talk about the spark plugs in your car. The spark plug gives off this little spark of basically static electricity. Well, you introduce static electricity into gasoline that's already hot and is mixed with oxygen, and what you get is a little miniature explosion. And that miniature explosion is what drives the piston down right here. Poof, there it went. And then your fourth stroke is an upstroke. That piston comes back up and pushes all that exhaust, the burned up fuel and oxygen, now it's carbon dioxide, pushes it back out of your chamber. So that's an example of how work can be done to change kinetic energy. Now, you'll hear this word entropy once in a while. Okay. Entropy is a measure of disorder in a system. In any system, to make it nice and neat and orderly, you have to do work. Think about cleaning your room. It takes a lot of work to clean your room. Okay. However, entropy says that all that nice work that you did to get things looking nice and neat, if left to itself, that neatness will go away. It will become disorderly. Think about it. If you don't actively clean your room every day, a week later, I bet it's a mess. So now let's take this in terms of energy. Entropy, we talk about usable energy and unusable energy. So if you have usable energy, it's energy that you can harness to put it to work somehow. Okay. So in that last example with the car piston, the car engine, that incoming energy in the form of chemicals, fuel and oxygen, that was a usable form of energy. We can do something with that. At the fourth stroke, when we shove the exhaust back out of the engine, that's unusable energy. All that is heat. Now, I could imagine some wise, intelligent person figuring out a way that as that exhaust left the engine, maybe it could be put to work. But eventually it gets to the point you can't do anything more with that. All it is heat. All it does is warm up the car parts, warm up the air as it leaves the car. But it's not actually doing anything useful anymore. That's what we talk about entropy, going from a usable form of energy to an unusable form of energy. All right, the second law of thermodynamics. Second law of thermodynamics is really simple. Energy transferred as heat always moves from an object at hot temperature to an object at a cold temperature. So high temperature to low temperature. It's never going to spontaneously heat something up. That energy always has to come from somewhere. But an object will spontaneously cool down. Also, I want to take a minute right here and explain something to you. There is no such thing as cold. Right, you heard me right. There is such a thing as heat. Heat is the measure of energy being transferred. There's such a thing as thermal energy. That's how we measure the movement of the atoms and the molecules. There's no such thing as cold. Cold is the absence of that energy. So if you feel cold, you're not feeling a thing, you're feeling an absence of a thing. You're feeling the absence of thermal energy. Okay, I want you to stop right now. Need to go to the kitchen. And here's what I want you to do. Listen to all the instructions before you start. With your parents' permission, of course, because you're going to be using the stove, just put a little saucepan of water on the stove and let it come to a full rolling boil. Now, while it's boiling, you can turn the heat off, but do this fast because I want it to still be boiling when you do this part. Add a large amount of ice. I'm not talking about a single ice cube. A good handful of ice. Now, please listen to me. Do not just throw the ice in. That water is boiling, it will splash out, it will burn you. My suggestion would be to get a big serving spoon or a soup ladle, put the ice in the spoon or ladle, and lower it in. Do it safely. All right, you're going to type up what happens as soon as the ice hits that boiling water. Is it still boiling? Okay. And then you need to explain to me, in terms of the second law of thermodynamics, what happened when you added that ice to the water. Now, that's going to be part of your homework assignment, and that assignment will roll into the one from last time, and that will become a lab grade. So make sure you do that properly. I want it written in paragraph form. There's a separate link on Google Classroom where you can get definite instructions and you can submit your work. All right, that is all you need to know about thermodynamics for now. So good luck. Let me know if you have any questions. You can be happy. There's no math associated with section 3. At this point, you need to start working on your chapter 14 review. That's posted. We do have a test coming up next Tuesday. So this is Thursday's assignment, test on Tuesday. I would really strongly suggest that you get the chapter review done no later than Monday morning, and meet me in tutoring on on Monday afternoon, so that if you need help, you can get help from me. All right. Take care. See you all later. Bye-bye.